So in the last session we started with describing the describing function, and we'll now find out describing function of some commonly occurring nonlinear elements. So we'll start with the on-off relay. Or we can simply say on-off nonlinearity. So the on-off relay, is simply, so we'll be having a system where we will be applying an input, then we'll be having the non-linear element based upon which we'll be getting an output. The input is specifically a sinusoidal signal. The non-linear element here is the on-off relay. So superimposing the input on the non-linear element, we'll be seeing what will be the output in this case. So on-off relay is something, the behavior of a on-off relay is something like this, where for all positive values of x we'll be getting, it's not necessary we'll be having a magnitude of 1, we'll be having a magnitude of plus m, and for all negative values of x we'll be having a magnitude of minus m. And the input that we are applying to this is a sinusoidal input. I will be showing the sinusoidal input like this. So this is the characteristics of the on-off relay. This is our input to the system, that is the sinusoidal input, and superimposing these two, the magnitude of this sinusoidal input is x by that we have already established yesterday. So superimposing the input onto the on-off linearity, we'll be getting the output, and the output waveform therefore will be the magnitude of the output of this on-off linear, the output will be having a magnitude of m, a peak magnitude m. So we have, this is our output. We need to find out its fundamental component, and that will be doing actually using the Fourier analysis. This is our output. So using the Fourier analysis, we'll be able to find out the fundamental component of this output waveform, and that fundamental component will actually be a sinusoidal waveform, y1 of omega t, that we need to find out. So if this is y of omega t, we can therefore say y of omega t is equal to plus m and minus m. It will be equal to plus m for 0 to omega t to pi, where pi will be actually determined by the input sinusoidal function 0 to omega t to pi, and from pi to 2 pi the value of omega t will be equal to minus m. Value of y of omega t will be equal to minus m. Now we need to check for the symmetry and whether this function is an even function or an odd function. Looking at the waveform itself, we can directly say that the function has odd symmetry, and it is also half wave symmetrical. That means y of omega t is equal to y of minus of y of omega t plus minus pi. So around, so if you look at beyond plus pi, the y changed from plus m to minus m, therefore it is an odd function, as well as it is symmetrical around the half wave, not around the quarter wave. So this is this we know about the system, and for an odd function we have to find out only b of n. A naught and a n will be equal to 0. So if our function is odd, we need to only find out b of n. That is actually b of 1 only in this case, because we are only dealing with the fundamental component. So for this case, what we know is b of 1 will be equal to 2 by pi 0 to pi. We are taking it around the time period that is only 1 by pi. Okay, 0 to pi y of omega t sine of omega t d omega t. That means 2 by pi this becomes equal to after integration minus m cos of omega t 0 to pi, where y of omega t is equal to m from 0 to pi. Substituting the limits, 2 by pi minus m, cos of pi is minus 1, cos of 0 is -1, so this becomes minus plus m, this becomes actually equal to 2m. So this is 4m by pi. So for this particular case, b1 is equal to 4m by pi. What is phi 1 going to be? Phi 1 will be equal to tan inverse of a1 by b1. Since a1 is not 0, indeterminable in this case, so it is actually equal to tan inverse of 0. That is actually 0 degrees. So therefore y1 of omega t can be written as, the Fourier expansion can be written as a naught plus summation of n is equal to 1 to pi. Since we are not going into this, we are only looking at the fundamental component, that's y1, so it will be only a naught plus a1 plus b1. A naught is 0 in this case, a1 is 0 in this case, this is equal to b1. b1 therefore will be equal to this is therefore be equal to b1 sine of omega t. b1 is what? b1 is 4m by pi sine of omega t. By Fourier transform, y1 will be equal to a naught plus a1 sin cos omega t plus b1 sin omega t. Only a1 and b1, no summation, because only we are dealing with the fundamental component, that's y1. Since a naught and a1 in this case is 0, so this is b1 sin omega t. b1 we have already found out, it is equal to 4m by pi. So y1 omega t is equal to 4m by pi sine of omega t. So this is y1, and phi 1 is equal to 0. So regarding the describing function that we discussed yesterday, we have defined the describing function as n equal to y1 angle phi 1 divided by x, where x is the magnitude of the sinusoidal input. So in this case what we are having is describing function of this on-off relay we can therefore write this equal to y1 angle phi 1 divided by x. y1 is 4m by pi the magnitude only 4m by pi angle 0 divided by x, that is the magnitude of the sinusoidal input. So therefore n x equal to this is a representation of the describing function, like we write g of s, like we write g of z. This is n of x is the representation of the describing function, therefore is equal to 4m by pi x. Angle is 0, so we can ignore it, we can need not mention it. So this is the describing function of the on-off relay, 4m by pi x. So if we look at this, if we make a graph, if we plot a graph between n of x and the graph between m divided by x, capital X, we'll get a straight line. So we are saying that y is equal to mx, fine, equation of a straight line. where y in this case is n of x, axis is m divided by capital X, and m in this case is 4 by pi. That means the slope of this line is 4 divided by pi. So the graph of the describing function between and with respect to m divided by x is a straight line whose slope is equal to 4 by pi for an on-off relay. So we'll be actually looking at these plots. We'll be looking at the plot of n of x with respect to the magnitude of the sinusoidal input as well as the magnitude of the on-off relay itself. We'll plot those two graphs. We'll plot this graph and we'll see what this plot will be. In this case, it is a slope. It's a straight line having a slope of 4 divided by pi. So this is the describing function of an on-off relay. So using this y1 of omega, using this equation n of x equal to 4m by pi x, we can describe the dynamics of an on-off relay that can be used that may be useful for us at for analysis at various occasions. Next, we'll find out the describing function of a relay with hysteresis. Relay with hysteresis means an output like this. Let the magnitude of the output be m, and the width of this be let this be h, this point be minus h. So we are superimposing a sinusoidal waveform on this. So what will be the output in this case? From 0 to h, let this angle be alpha here on this graph. From 0 to alpha, y of omega t, it will be having 3 different values. One is from 0 to alpha, another one from alpha to pi plus alpha, and Then from pi plus alpha to 2 pi plus alpha actually, but we are concerned with 2 pi only. So what will happen from 0 to pi, 0 to alpha, the output will be minus m. From alpha to pi plus alpha, that's actually beyond this region on this curve, the relay, the non-linearity is actually working as a relay, and for a relay we saw that the output will be equal to plus m, and this will continue till pi plus alpha. Beyond pi plus alpha, this will again become equal to minus m, where pi plus alpha actually represents this point. So what is happening actually in this curve is, between this hysteresis period, your graph is actually your graph, say for example we are taking this as an initial point, our graph is going in this direction, but when it comes back it does not traverse this direction, it traverses this direction. That's actually the concept of hysteresis, and it follows this path up to pi plus alpha. So beyond pi, beyond this region, again it will be equal to minus m up to 2 pi. When it comes back, it does not go back through this path, it traverses this path. So until this point, that is actually 0 to alpha included, the system will be still remain, the output will still remain minus m. Only at alpha this will switch over to plus m. It will not traverse this path at pi plus alpha, it will traverse this path. That's actually what happens with hysteresis. Our original path is not traversed, a different path is obtained in either directions. So from 0 to alpha, this will have been actually continuing from some previous cycle that would have already taken place. So before that, and therefore from 0 to alpha, this path will be traversed. That means output will be minus m. From alpha to pi plus alpha, then it will be simply working from alpha to pi minus alpha, it will actually be simply working as a relay. From pi minus alpha again, that's actually at this point, to pi plus alpha, it will traverse this path, that is plus m path again. So that means in totality from alpha to pi plus alpha, it will travel the path of magnitude plus m. And then from pi plus alpha to 2 pi, it will 2 pi minus alpha rather, it will work as a relay in the negative half region. From pi minus alpha to 2 pi, and then 2 pi to 2 pi plus alpha, that's actually this region that will be covered of the on-off linearity. So therefore our output looks something like this. So this is alpha, so somewhere around here will be pi, so this is pi plus alpha, so up to 2 pi it is something like this. This will actually go up to 2 pi plus alpha, but we are dealing with only a time period of 0 to 2 pi, so that's sufficient for us. So this is our y omega t. Now we need to find out now we need to do the Fourier analysis of this function. So looking at this function, y of omega t is actually a shifted waveform by alpha, and therefore it is neither odd nor even function, but it has a half wave symmetry. Y of omega t is neither odd nor even, it is half wave symmetrical. With the half wave symmetry, a naught is equal to 0, but a1 will not be equal to 0 because it is not an odd function exclusively. So we have to find out both a1 in this case as well as b1. a1 will be equal to y of omega t a1 will be equal to 2 by pi 0 to pi y of omega t cos omega t d omega t, and v1 will be equal to 2 by pi 0 to pi y of omega t sine of omega t d omega t. So a1 0 to pi 0 to alpha, it will have the value minus m. From alpha to pi it will have the value plus m. So you have to substitute those two. You have to find out this integral. You will come up, you will see this will be equal to minus 4 pi by m sine of alpha, and again same with b1. This will be equal to 4m by pi cos alpha. So we have found out both a1 as well as b1. Therefore y1 will be equal to under root of a1 square plus b1 square. So you can substitute the values. It will come out to be equal to 4m by pi, and phi1 will be equal to tan inverse of a1 by b1, which will be in this case simply equal to minus of alpha. So therefore the describing function n of x will be equal to y1 angle phi1 divided by x. So this will be equal to 4m by pi, angle is minus alpha in this case, divided by x, or we can write x here. One more thing, we can look at the graph and see that alpha this width here, so this was equal to 0 to h, this width will also be you can say this is equal to 0 to h. We can therefore say alpha is equal to sine inverse of h divided by x. We can calculate alpha equal to sine inverse of h divided by x from here. So we have obtained the describing function of a relay with hysteresis. So we are getting 4m by pi x angle minus alpha, or angle we can say sine inverse of alpha by x, h by x. So again plotting plot n of x and plotting n of x with respect to m by x. So we have here an angle of minus alpha, where alpha is equal to sine inverse of h divided by x. So n of x is equal to m by x into 4 by pi angle sine inverse of minus h by x. So once you plot this, what you will obtain is a drooping curve because of the negative angle that is here. This will be having a slope of 4 by pi again. only difference is that because of this angle minus alpha, that's actually equal to sine inverse of h by x. So x is again in itself the input quantity, so we could have shifted that also to the left hand side with nx. So we are getting a curve, a drooping curve because of the negative sign, and this will be somewhat sinusoidal curve. So we this is the plot of describing function with respect to the magnitude of the non-linear element. So we have done two. This will be corresponding to phase angle of 90 degrees. So, and this will be corresponding to phase angle of 0. So we have done two describing functions today, so we'll be continuing next time.